few. We've got frustrating apps, Yarwin. We've got repairing apps, Yanji, and then we've got diffuser, which is you. Yes, that's the order that's in the research.
Okay, I didn't have the same order, so okay.
Really?
Sure.
Okay. Oh yeah, the Clouder ones aren't ordered. Recording has started, so we'll stay connected. I think that means we're underway, Salome. I think
should I start?
So, well, let me get underway. So, hi everybody. Welcome to this session on apps and App Store analysis at ICSE 2022. We'd love to be with you in person, but all the problems of the world conflate to make that a bit on the difficult side. So, hopefully some of you can make it in person in a couple of weeks' time. Got 4 great talks this morning for you, all on, funnily enough, app and App Store analysis. We'll have Jordan is going to go first, talk about Juicify, which is a step towards Android code unification. Each presentation is 5 minutes. Any questions, put in the chat, but we'll do the questions all together at the end. So we have the 4 presentations, then an open question session. If you've got a particular presenter you want to ask a question, please put their name in the start or something of your question so we know who to direct them to. All right then, so Jordan's a 3rd-year PhD, Uni Luxembourg, currently visiting Uni Washington in the US, and he's going to have 2 goes this morning. So I'll hand it over to him now to share screen and talk about Juicify.
Yes. Can you see the screen?
That's
yes.
Great. Yep.
Yes.
And full screen right now. Okay. So hello guys, and welcome to this presentation. I'm going to present the paper entitled Juicify. This is a joint work you can see on the screen. But first, I'm going to present myself very quickly. I'm Jordan Samy, a PhD student from the University of Luxembourg, and my work is mainly focused on software engineering and software security. So the main focus of my work is to reason about the following question. How can I take advantage of the Android framework to hide code execution from existing analyzers? This drives my research direction and work. But is it important? In fact, this year at ICSE, a very interesting paper explores the different ways that attacker can use to enter the Google Play. One of which is to use native code. Indeed, the author found that more than 25% of apps split the malicious code between the Java bytecode and the native code. And they say that there is a need for tools to take that into account. Because the problem is that most analysis, they overlook native code because this is harder than analyzing bytecode. And where they don't, they do not yield an explicit unified model. Hence, one cannot perform a generic analysis. This is a simple example of native code usage. We have the Java part and the native part. We can see that both are different. According to Lee and al., most of static analysis are built on top of the SOOT framework. So therefore, our works aim to fill the gap in whole app analysis in the SOOT ecosystem by researching means to build a unified model of Android code. So for that, we propose Juicify, a step toward building a framework that breaks the bytecode native boundaries for Android apps and therefore copes with a common limitation of static approaches in the literature. So the idea is to unify both representations so that we can run any downstream analysis. So here is an example of Java bytecode control flow graph on the left and a binary code on the right. Existing approaches mainly perform separated analysis and bridge the results together. Our ambition is to propose a unified model on which any downstream analysis can be built upon. So let's see our approach to reach this ambition. It's divided in 3 parts. The first one is called native disclosure, that relies on symbolic execution. The first step is to construct the native call graph, then to extract the native method information. For example, here you can see the signatures. We spot we spot bytecode to native calls and match the native counterpart. For example, here the call to native get IMEI.
Sorry about this, Jordan. Are you advancing your slides? Mine's still stuck on the first one. I don't know about others.
Is it? Oh,
Can you see Jordan's updated slides?
Yeah, seems to be stuck in the first.
Ah, it's stuck. Oh, sorry. Should I start over or?
I wonder what making it stuck. There, now it's on approach. So.
Oh, I'm sorry. What should I do? Should I start over, or do you want me to continue?
let's rewind back to that and zip through up to where you are now would be great. So it now seems to be scrolling okay.
So I start over, right?
Yeah, go for it. Yeah.
Yeah, sorry for that. So it's not full screen, but okay. Anyway, I will start over my crowd. Okay. So hello and welcome to this presentation. I'm sorry for that. I'm going to present the paper that is entitled Justify, a Step Towards Android Code Unification for Non-Static Analysis. I will skip this part. I already told about it. So the main focus of my work is to reason about the following question. How can I take advantage of the Android framework to hide code execution from existing analyzers? This drives my research directions. But we can ask ourselves, is it important? In fact, yes, because this year at ICSE, a very interesting paper explores the different ways that attacker can use to enter the Google Play, one of which is to use native code. Indeed, the author found that more than 25% of apps split the malicious code between the Java bytecode and the native code. And they even say that there is a need for tools to take that into account, of course. The problem is that most of analysis overlook native code, and where they do not overlook native code, they do not yield an explicit unified model. So analysts cannot perform generic downstream analysis. This is a simple usage of how native code works. You would declare in the Java part a method, a function that is actually implemented in C, and you can call it here. You can see the native get IMEI call. So according to Lee and al., most of static analysis are built on top of the SUIT framework. So therefore, our work aims to fill the gap in whole app analysis in the SUIT ecosystem by researching means to build a unified model of Android code. So bytecode, Java bytecode, and native code. So for that, we propose Justify, a step towards building a framework that breaks the boundaries between bytecode and native code. The idea is to unify both representations so that we can run any downstream analysis. For example, a data flow analysis. So here is an example of Java bytecode control flow graph on the left and binary code on the right. Existing approaches perform separated analysis and bridge the results together. Our ambition is to propose a unified model on which any downstream analysis can be built. So let's say our approach to reach this ambition. It's divided in three main parts, and the first one is called native disclosure. It relies on symbolic execution. So the first step is to construct a native call graph. We rely on external tools called Anger for that. And then we extract the native code, the native method information, like the signatures. Third, we spot the bytecode to native calls and match the native counterparts. For example, the native get IMEI call here. Fourth, we search for bytecode method called from the native code. For example, here the get device ID is called from the native code using reflection-like mechanism. The second part is the call graph component generation. First, we prune the native call graph and only keep nodes that are reachable from the previously computed entry points. Second, we construct the bytecode call graph using Spark that is implemented in SUIT. The third part is the unification of both worlds. We transform the native call graph into the SUIT representation, and then we patch it with the link in bytecode to native and native to bytecode functions. So we connected the both call graph together. So these steps allow to uncover previously unreachable nodes in the bytecode call graph. So before applying Justify, this would be the call graph generated by SUIT for the first piece of code I showed you earlier. We can see that we can only see the call to a function called native get IMEI. But we do not know what it does or what are the Android APIs that are called. After Justify, we can see an improvement. We can see the call graph is augmented, and we can even see the call to the get device ID function. So as our ambition is to propose a unified model for both bytecode and binary, we cannot stop at the call graph representation, which would not be enough. So for that, we have to find a solution to approximate, and we relied on instrumentation and code generation for that. There are more information in the paper if you are interested. This would be an example of, this would be the code generated by Justify for the previous example for the native get IMEI from call to get device ID here. So we performed some experiments. You can see the setup in the paper, and I will just give here the main results. So native code is well spread in Android apps, as confirmed by the ICSI paper I told you earlier. Native disclosure module outperform existing approaches, justify boost static intent analyzer FlowDroid by revealing leaks, data leaks that flows through the native code. So we have seen that Justify indeed improves the call graphs, and it even reveals sensitive data leaks across bytecode and binary code in real-world applications. So I thank you for your attention. You can see a summary of the work on the screen. Do not hesitate to contact me. May you have any question about the approach, the tool, or anything. Thank you.
Thank you so much, Jordan. All good. So we're going to go on to the next presentation now, which is by Yawen Wang. He's from the Institute of Software, Chinese Academy of Sciences, Beijing. And he's going to be telling us about where is your app frustrating users. Thank you very much, Yawen.
Okay, can you see my screen?
That's good.
Okay. Hello everyone, my name is Yawen Wang. I am a PhD student from Institute of Software, Chinese Academy of Sciences. Thank you for listening my presentation about our recent study. The title is Where is your app frustrating users? This study is about information extraction from app reviews to facilitate developers to improve the quality of apps. Users often write reviews of apps to provide valuable information to developers, such as user experience, bug reports, and so on. So, firstly, let us look at what users are complaining about in app reviews. The first level is what aspects. That is the high-level topics or aspects of the reviews. And the second level is where aspects. Users are complaining about specific app features, and they think these features might have problems. And the final level is other aspects, mostly are some trivial information. So in this study, we focus on the where aspect. That is which specific app features the users are complaining about. In this study, we define phrases buried in app reviews which reflect users' complaints about certain app features as problematic feature. And for example, the problematic features from the left three reviews are these three phrases. The problematic features have many potential application scenarios, such as bug location, bug recommendation, GUI testing, and competitive analysis. So the question is how to automatically extract problematic features from app reviews. And we propose an approach named Sira to extract, cluster, and visualize the problematic features of apps. And it has 4 steps. First, it pre-processes the app reviews crowd from online app markets to obtain the clean review descriptions and the review attributes. And second, it builds and tunes a phrase extraction model to automatically extract the feature phrases. The model combines the review descriptions and the 2 review attributes as input to better model the semantics of reviews. And third, Sira clusters the extracted phrases with a graph-based clustering algorithm to summarize the common aspects of features based on their semantic relations. And finally, it presents a realization view to illustrate the summaries and compare the features among different apps. As for the dataset, we use the reviews of 6 apps from 3 categories as our experimental data. And we answer the following 3 research questions. RQ1 investigates the performance of problematic feature extraction. RQ2 conducts a comparison with Sira's 3 variants to demonstrate the contribution of each review attribute in phrase extraction model. RQ3 investigates the performance of Sira in problematic feature clustering. And for RQ1, Sierra outperforms 4 baselines on all metrics in extracting problematic features. And we also present some examples on extracted problematic features by different approaches. And for RQ2, we construct 3 variants of Sierra. And the performance achieved by adding both of the attributes is the highest, further indicating the advantage of our model design. And for RQ3, we use LDA and k-means as the baselines to evaluate the performance of clustering, and Sierra outperforms 2 baselines on both metrics. And finally, we apply Sierra on a large-scale dataset to obtain the visualization. The figure shows the distribution of problematic features of different categories. And this table presents the representative problematic feature of each cluster in the last figure. And this is the conclusion. And that's all of my presentation. Thank you.
Thanks so much for that, Yawen. That's great. All right, now we've got our third presenter for this session, Yanji Zhao from Monash University here in Australia. And she's going to be telling us about her work on automatically repairing compatibility issues in Android apps. I'll hand it over to you, Yanji.
Hello, everyone. I will introduce our paper towards automatically repairing compatibility issues in published Android apps. And I'm from Monash University, Australia. And first, I will introduce the background. The serious fragmentation problem of Android has caused severe compatibility issues for the Android ecosystem. It is many different Android versions, including official and customized, running on different devices released by hundreds of manufacturers. Android phone users often find that some apps can't be installed on their devices or can be installed but will crash later on if a specific function is reached, leading to poor user experience. Actually, there are over 1 billion Android devices no longer supported by Google, and there are more than 24,000 distinct device models running on more than 10 different API levels in the market. Each API level supports thousands of APIs. Therefore, the users of those devices will likely encounter compatibility issues, especially when they want to leverage the latest Android apps, leading to serious problems in the mobile ecosystem. And about the motivation of this paper, as mentioned, the heavy fragmentation of the Android ecosystem has induced many types of compatibility issues in Android apps. Our research community has spent lots of effort on disclosing such issues, including at least the following 3 types: OS-induced, device-specific, and inter-callback. The first one is one of the most common types of compatibility issues. The issues are caused by the evolution of the Android framework. During framework evolution, new APIs are regularly added to the framework, and existing APIs are also regularly deprecated and removed. The example given in the figure shows a deprecated API issue. API get type and is deprecated at SDK level 28. And on devices running SDK versions larger than 28, it is recommended to use API has transport. And the second type is device-specific. These compatibility issues are associated with specific devices running customized Android systems. The problematic apps will only crash on certain devices, but behaving normally on others, despite all the devices running the same Android framework version. Present such an example. The API set recording hint depends on the conditional statement that checks the device identifier against Nexus 4. Only the condition to be true, the corresponding app is indeed running on Nexus 4, the API will be executed. And the third type is caused by the changes to Android system callbacks, also known as lifecycle methods. Such system callback methods are predefined by the Android system and will be directly executed when certain conditions are satisfied. The listing illustrates such an example. Lines with a plus sign fixed for this incompatibility. The unattached context callback method is only introduced from API level 23. If this code is running on smartphones with earlier API levels, this callback method will not be executed. So the M activity field will not be initialized and its usage will likely throw null pointer exceptions. And as for the repairing work, existing approaches of the first type all come with some limitations. For example, COSI involve only attempts to fix incompatible APIs within a single method. Their follow-up work Android involve fix this limitation.
Need to finish, Angie.
Okay.
All right, thanks very much. Just 5 minutes, remember, everybody. So last talk now is Jordan again from Uni Luxembourg. He's going to tell us about Diffuser, uncovering suspicious hidden sensitive operations in Android apps. Thanks very much again, Jordan.
So I guess you can see the screen. Yes.
It's good.
It's good. Okay. Let's go again. So hello and welcome to this presentation again. I'm going to present the paper entitled Diffuser, Uncovering Suspicious Hidden Sensitive Operations in Android Apps. I'm going to quickly present myself because I already did, but for those that were not here. So I'm Jordan Samy. I'm a PhD student from the University of Luxembourg, and my work is mainly focused on software engineering, software security, and also Android apps analysis. So the main focus of my work, as before, is to reason about the following question. Still the same question. How can I take advantage of the Android framework to hide code execution from existing analyzers? Is it important? As I said at the previous presentation, yes, it is. The proof is that at ICSI this year, a very interesting paper explores different ways that attackers can use to enter the Google Play. One of which is to use specific conditions to evade dynamic analysis. Indeed, some applications use conditional checks to activate or not their payload. So I really encourage you to have a look at this paper. It's really interesting. So the focus of this paper is to uncover logic bombs in malware. Logic bombs are just code that are triggered under very specific circumstances. They are mainly used to bypass dynamic analyzers because the malicious code is meant to be executed under specific circumstances. So the malicious look by dynamic analyzers. So given that this is a hard problem, it remains unsolved and we need new approaches to solve this problem. So that's what we are trying to do here. Also, logic bombs are a specific case of hidden sensitive operations because they are malicious, and hidden sensitive operation might not be malicious nor intentional. Why is logic bomb detection hard? Look at this example. It will trigger some code given that the device is at a specific. If I tell you that this is a GPS app, this might be legitimate, right? For instance, for speed enforcement, zone detection, or something like that. But if this is a calculator, this might be suspicious. It really depends on the context of the app under analysis. So that's why it's so hard. In this work, we want malicious hidden sensitive operations. So our first step is to get suspicious ones. So our approach is divided in two parts. First, identifying potential suspicious hidden sensitive operation entry points, then our step. So we rely on tent analysis to track those data of interest to if statements. For instance, here, the build model field is used to take a decision and trigger the malicious code, the red nodes here on the left. Thanks to the tent analysis, we are able to track the model information through the program and spot if statements of interest for our study. But how do we decide what are our sources of interest? For that, it has been shown in the literature sensitive operations are often triggered using system inputs or environment variable. You can have a look at the paper for our systematic study. Once we have our suspicious hidden sensitive operation entry point, the next step is trigger. This is the anomaly detection engine. The goal here is to learn what is a normal, or let's say a benign trigger through benign applications and automatically discriminate suspicious checks in malware applications. So the idea is to spot suspicious hidden sensitive operations for which the likelihood to be a logic bomb is high. So we use specifically crafted features that add malicious semantic, and they are described also in the paper. So we have an app, we try to get the entry points, then when we have the entry points, we extract the features, and then we use our anomaly detection engine that try to see if this is a suspicious check or not. So we perform a bunch of evaluation, and here are the main results. The anomaly detection step reduces the search space, which is really important because at the end, finding in the current state of the art a logic bombs is at the end done manually because we are not sure, so we have to manually analyze to see if this is a logic bomb or not. So we have to reduce the search space, and the anomaly detection is a good idea for that. Diffuser execution time is really low. It's about 35 seconds per applications. And a diffuser contributes to detecting logic bombs within suspicious hidden sensitive operation. We have shown that almost 30% of them, after our manual analysis, are indeed logic bombs. We compared against the state-of-the-art logic bomb detector TriggerScope and show that we have better results. We also show that diffuser reveals potentially harmful applications in benign apps and even contributed to remove 8 adware from the Google Play. So this is the main results. I thank you for your attention. You can see a summary of our work on the screen. So if you have any question, you can contact me. Thank you.
Thanks so much, Jordan, for a second time. Well done. All right, so now we're going to have an open question and answer session. If you have any questions, it's probably easiest for us to coordinate them, put them in the chat. Well, we've got any questions at the moment, Salome? I don't see any. Alrighty. I'm going to ask a question for Jordan then on your first page. Sorry, Jordan, go ahead.
Can we also ask questions?
Yes, you can ask questions of other presenters. You've got a question?
Yeah, I had a question for Chao. Do we say Chao? I'm sorry, I don't know how to pronounce it.
Chao.
Yeah.
Yes.
Cool. Go ahead.
You didn't have the occasion to finish the presentation, so I was wondering how you automatically repair those issue that you were presenting in Android apps.
Oh, our tool it is named Repair Droid. It first takes some fixed templates and input, and the format of these fixed templates is defined by us, and then Repair Droid templates and use Suit to instrument the Android apps, so it can we have a bug location module, and then we use Suit to instrument
the app. Oh, okay, I see. Thank you.
And I also have a question for you. The Juicify paper. Yeah, the Juicify paper. So can Juicify provide a complete call graph for static analysis?
Complete is I cannot say it's complete, but we are trying to make it complete. So the idea for the moment is that for the bytecode part, we rely on Spark, which is implemented in Soot, which is a really good approximation of the real runtime call graph, let's say. And then we use another tool, which is Anger, to generate another call graph for the native part. And this is not the same as for bytecode. This is the same paradigm. So this tool has some approximation also. If you use another tool that generates another call graph for the native part, you will not have the same. But we decided to use this one because it's well known, it's well used. And then we connect the parts. And we connect the parts based on the results of our symbolic execution. So of course, I will be honest, I don't think it's complete. It will never be complete, but we are doing our best for that, okay? We are actually improving the call graph by adding the native part, yeah.
So can FlowDroid benefit from Juicify too?
Yeah, of course. We show that in the paper, actually. We have crafted several applications with 4 scenarios with leaks that flow through the bytecode and the native. And in the paper, we show that thanks to Juicify, FlowDroid, when you apply Juicify and then FlowDroid, we see that FlowDroid can detect the leak, both the bytecode and native part. So this was really, really interesting. And we even find some leaks in a real world application.
What's your plan for future work to improve the completeness?
Yeah, we are actually working for the moment on the instrumentation part, because except for the call graph, we have to also, let's say, populate statements for methods, okay? Because when you only work at the call graph level, you have method shells, let's say, with no statements. So the idea is to populate that based on some other approximation. And for the moment, the approximation we use has some problem because the number of statements can explode. We are relying on some combination, but we are exploring currently a method to reuse the results of the symbolic execution for having a more over approximation of native functions behavior that we import in Soot.
Okay,
that's great. Thanks very much, Jordan. And
thank you for the question.
Question in the chat for Yarwin. Do you understand the question, Yarwin? Can you answer that for Peter?
Okay. Where is the question?
Okay, I'll read it out to you. Did you explore a prior filtering step whereby whole sentences are classified as bug report or not?
Yeah, if you need any clarification, I'd be happy to clarify as well.
You mean the potential application scenario?
From the literature, there's lots of sentence level or review level bug report, non-bug report sort of data sets, right? So there's been stuff by like kind of Malaysia, Guzman, and things like that. So I can imagine as a prior filtering step, first of all, saying, does this contain any bug reports? First of all, before then identifying the issues. Did you explore that at all, or was there a reason you not to do it?
Okay. Okay. Actually, we treat the phrase extraction task as an NER task. So if when you recognize the phrase, the NER task can give you a tag that which tells you the classification of the phrase. Actually, the problematic feature in our work is the single one classification of the phrase.
So So I saw it's at this kind of new, more granular level where you have individual, phrases posed as an NER task. But I can imagine, first of all, just doing a prior filtering step, because there are already quite a few data sets that are not at your granular level, but at a sentence level, where you could potentially say, oh, okay, first of all, is problematic description contained within this whole sentence? And then
actually, the reviews have their ratings. Actually, in our data we use most of 1-star ratings reviews.
Okay, so that's a kind of filtering step as well. Okay, I can imagine that, but yeah, okay. I wonder if you could then further kind of boost performance by having I don't know, using. I mean, I suppose it's tricky to use other data sets as well. They might have domain adaptation issues. But, yeah, I can imagine perhaps like doing some sort of taking the 1-star reviews and then only finding the ones that have bug reports. That, like, you could take spam out, for example. Lots of stuff that just says, "Oh, this app sucks," or all the useless reviews.
I think it's a really interesting idea. I think the other one is sometimes reviews have positive and negative things in them. So how do you separate them out is an interesting challenge as well.
Yeah. I think that's probably one of the most interesting things about Yawen's work, is that it is so granular. I really like the idea of being able to pick out individual phrases, say this is what's really is annoying to people. I think that's why it's kind of a really cool piece of research. But yeah, thank you very much for answering. Yeah.
Okay. Actually, I cannot catch all your questions. So you can email me for detailed discussion.
Thank you very much. Am I quite echoey in here?
You are echoey, but don't worry too much.
Try and get that fixed out for next one. But yeah, I'll get you on the email then. Thank you very much, sir.
Okay.
Yeah, so all the presenters will be available on email. Their details are in the researcher program if anyone needs to get in contact. Are there any other questions from audience members? Okay, Pei asks, did you contact the developers, Yawen, to ask or to help improve the app by your findings? Yawen?
I
I'll say it again. Did you contact the developers to help improve the app by your findings? So if you found an app that's got some frustrating issues, did you kind of try and contact any of the app developers and give them some feedback from your analysis?
Yeah, we actually do some empirical study, and we think you can say the last step of our approach is a visualization step. So we have a visualization tool, and it can help the developers know what they want. Yeah.
Great, thanks for that. Question for you, Yanji. So you showed us a number of compatibility issues that need to be addressed. Are there any specific ones that can't be addressed by your tool at the moment, and your ideas for ways of addressing that?
Yeah, maybe in practice, there are some cases that the repair droid can't search the certain object it needs to fulfill the parameter list of the replacement API. Then it will stop. Yeah. But
thanks for that. Similar question for Jordan on your diffuser. What sorts of hidden operations can't currently be detected, and any thoughts about where to go?
Yes, that is a very good question, and we are currently working to improve that, because hidden sensitive operations can be triggered not only with if statements, but with other kind of structures, right? In this paper, we specifically focused on conditional statement that rely on if statements. You can imagine switch case or something like that. But there are some other mechanisms in the Android framework that can allow to trigger some pieces of code under specific conditions. For example, job-like mechanisms. You can trigger a renewable object under specific circumstances. For example, at a given time or a date, or if the device is currently charging or something like that. So that can be used also to trigger hidden sensitive operations. But of course, in this paper, we only relied on the we only tried to detect conditional statement, if statements, exactly. Thank you for the question.
That's great. Thanks, Jordan. Any other questions from either presenters to each other or audience?
Actually, I have a question. Yeah, I have read all the 3 papers in this session, and I think they are good work, first of all. But for me, the other 3 papers in this session are totally different from ours, and your work all focus on bug detection based on something like Android package and something like native code and bytecode. Actually, I'm not very familiar with these details, and my research mostly focus on requirement tags, user feedbacks, or issue reports, and something like written in natural language. And so I am wondering if such user feedbacks about apps, for example, if app reviews can help your works, or you can say, are there any possibilities to make connections between user feedbacks and the static analysis on Android package? That's my question for the other 2 presenters.
Yeah, Yanji, Jordan, any thoughts on that? Would app review analysis help highlight compatibility issues or hidden sensitive operations or anything like, or problems with native code analysis?
Yeah, I think for our work, yeah, the user feedback indeed benefits. Yeah, because if we get the user feedback, and then we know maybe several types of issues that need to be detected or repaired, then we can do something based on the user feedback. Yeah. Thank you.
Okay. In my case, from Juicify, I don't think so, because this is more of a conceptual approach, but maybe for diffuser, because there are maybe some patterns that we did not consider, or let's say sources also that we didn't consider, even if we try to be systematic. But if for example, a user would provide a feedback and say that, okay, each time I go into that place, I have weird behavior on my in this application, for example. So maybe there is something malicious. Maybe he knows how to trigger it. So maybe we can manually find it and try to model this this pattern. But other than that, I don't know. I have to think more about that. But thank you for the question.
It's a great question about connecting these kind of 2 different approaches, static and dynamic, and kind of user feedback in various forms. Question for Jordan from Salome. How does Juicify deal with high false positive rates between the entry point connection between the call graph from Spark and Anger?
You mean how does Juicify deal with the other approximation? Is that the question from the call graph construction?
Yeah, maybe I was wondering, because when you have the analysis from the application and then you try to connect to the native, there is a lot in the connection. There can be a lot of positives to figure out what part of, let's say, a native library was used, so that you just utilize that part.
Yeah.
And I wonder how that works in your framework.
For the moment, so from bytecode to native code, it's there are two cases. You can statically or dynamically register native functions, okay, native calls. So for statically registration, it's quite easy because there is a naming convention, so you can pinpoint the exact function that will be executed. For dynamically registered, it's a bit harder. You are right. So that's why we use symbolic execution. And if the symbolic execution yields a false positive, for the moment, we don't filter. So if the link is a false positive, we will have a false positive for example, if we perform data leak detection. I mean, we do not filter the links. If the native disclosures returns, I don't know, 3 links from the bytecode to the native, we just take that into account and use them. And this is the same in the other side. In the other side, from the native to the bytecode, we also on symbolic execution, because for example, to call a bytecode function from the native code, you will use something that looks like reflection in Java. So this can also yield false positive. I completely agree, but same, we do not filter for the moment. I hope this answered your questions. I'm not sure.
Yes. So yeah, thank you. So the symbolic execution really worked well as an alternative of the static versus the dynamic. Is that a good understanding of your work?
No, I don't think so. We used symbolic execution in this case for several reasons, because statically analyzing assembly code is really hard. Also to reconstruct strings that are used to call bytecode method, because as I said, it's like a reflection, so it uses strings. So it's better to rely. It's better. Not in the general case, I agree. But for what we are trying to do, we have seen that symbolic execution seems to work. But if you have a really big application with tons of statements, this might be a bit harder. I completely agree. This is a limitation of our approach, the symbolic execution in both sides.
It's a classic limitation.
Yeah.
Alrighty, that's great. Thank you again, Jordan. Any further questions?
I have a question. For the HSO paper, so
yes.
How do you prepare the ground truth, and how do you ensure the validity of the assessment?
So we didn't build any data set, any benchmark for this approach, and there is no ground truth actually in the literature. There is now, because I will explain later. But we relied on the results of yielded by diffuser on applications in the wild. And as I said during the presentation, the only way to ensure that our results are correct or that it yields something interesting is to manually analyze that. So what we did is we just reverse engineer the applications. We try to spot the exact location of the code that is pointed by a diffuser, and then we correlate this information with antiviruses reports to see if the behavior that is triggered is indeed what is described as the malicious behavior. We try also to check if the if statement is really what is reported by diffuser, and if this is correlated, we consider it as a logic bomb. Is it the question? Yeah. So this is automatically. This is really hard, especially since we don't have any ground truth. But we have actually published another paper at MSR Data and Tool Track to automatically construct a new ground truth, a benchmark. So the idea is to take a benign application from the Google Play and to automatically infect them with a tool with known logic bombs. And we repack the applications. And those applications can be used then to compare different approaches. I will have to present this paper in several days. I don't remember when exactly. But if you're interested, you can.
Okay, thank you.
Thanks for that.
Thank you.
And have you tried any deep learning based maybe because you only mentioned one class SVM, yeah, in the paper.
Yeah, we wanted to perform anomaly detection and relied on a well-known. I'm not a machine learning, deep learning expert, so I had to rely on something that proves to works in the state of the art. So we used the one class SVM, and it seems to work. So we were happy about that. But no, we didn't use any deep learning approach. No,
Okay.
not yet.
Thank you. Thank you.
Thank you for the question.
All right, thanks very much. Well, I'm going to thank all the presenters. Yeah, I need to go to my next session. Cheer. Thank all the presenters for giving really good short talks and answering lots and lots of questions. Remember, the papers and some other media are online on the researcher.org page. And again, they're available on email for further, more detailed discussion if you need. Thanks again, everybody. Thanks, Salome, for helping coordinate, and have a great rest of the day / evening / night, depending wherever you are.
Great. Thank you very much.
Sí.
Bye-bye.
Bye-bye.